Welcome to 33 lecture in mechanics of materials. The last lecture we began looking at failure theories. We saw that the failure theories should be based on the stress more rather than the strain, and then we saw that there are two kinds of materials, one which are hydrostatic pressure insensitive to failure, which are hydrostatic pressure sensitive to failure. Okay. The materials which are hydrostatic pressure insensitive to failure undergo usually a ductile kind of a failure, and we were looking at failure theories for these kind of materials. We looked at Tresca criteria, which says that the maximum shear stress should be less than a particular value before the material begins to yield or fail. Okay. So, in particular we saw that the failure envelope for Tresca criteria is as shown here in the form of an hexagon, okay. And then we saw that this kappa, which is like a metal parameter, can be determined from a uniaxial test or from a pure shear test. In particular, if it is determined from a uniaxial test, it is sigma y by 2, and if it is determined from a pure shear test, it is tau y. Okay. So, we saw this in the last class. In today's class, we are going to look at another failure criteria, which is called as vonMises criteria. Okay. We are going to look at vonMises criteria. What this says is, we saw in the last class that a general form for failure surface or yield surface specification is a function of the form f as a function of sigma 1 d, sigma 2 d, sigma 3 d for hydrostatic pressure insensitive materials, or a function of k 2 d, k 3 d, where k 2 d and k 3 d are the invariants of the deviatoric stress, right. Okay. What the vonMises criteria says is, this k 2 d should be less than or equal to kappa, where this is again a material parameter. From our lecture 9, we know that k 2 d is nothing but 1 half trace of sigma d squared, which is nothing but 1 by 2 into trace of sigma d is sigma minus trace sigma by 3 identity multiplied by sigma minus trace sigma by 3 multiplied by identity, which is nothing but 1 half trace of sigma square minus 1 by 3 trace sigma whole square. Okay. This expression in particular for can be written as 1 by 6 into sigma 1 minus sigma 2 the whole square plus sigma 2 minus sigma 3 the whole square plus sigma 3 minus sigma 1 the whole square, when I represent sigma in terms of its principal values. Okay. So, this is k 2 d. Okay. Now, how do you find kappa? That is the question that we have to address next. How to find kappa? We will follow the same thing that we did for Tresca criteria. We will take a uniaxial state of stress, axial state of stress, for which it is sigma uniaxial 0 0 0 0 0, and for this you can compute k 2 d to be 1 by 6 sigma 1 square plus 0 plus sigma 1 square, which is sigma 1 square by 3. Okay. So, basically to make dimensionally consistent, let me call this as kappa square rather than kappa. Okay. So, k to d must be less than or equal to kappa square. So, this is sigma 1 square by 3. So, okay. So, sigma 1 now is sigma uniaxial squared by 3, that is the sigma 1 principal stress. Okay. Now, I know that when the stress reaches sigma y, the material has begun to yield. So, it is sigma y by square by 3 must be equal to kappa, that is the limiting value of the stress for which kappa square. Okay. That is the limiting value of stress for which the material began to yield. In other words, kappa is sigma y by root 3. Okay. Sigma y by root 3. Now, so the vonMises criteria reduces to, this implies vonMises criteria implies k to d is equal to sigma y must be less than or equal to sigma y square by 3, or I can rewrite this as square root of k to d must be less than or equal to sigma y by root 3. Okay. Now, let us do what we did before. Let us say I found this kappa from a uniaxial test and I want to predict what happens for a torsion experiment. Okay. So, sigma for torsion is just like what we did for Tresca criteria, same arguments 0 0 0. I am assuming only sigma yz to exist at a particular point. So, that will be tau tau. Okay. Now, for this I know sigma 1 is equal to tau, I know sigma 2 is minus tau and sigma 3 is 0, right. Okay. Now, what happens then, k to d becomes 1 by 6 2 tau whole square plus tau square which will be tau square. Okay. Now, this has to be lesser than or equal to kappa square, which is sigma y square by 3. Okay. So, the limiting value of the shear stress the yielding value of shear stress would be sigma y by root 3, which will be 0.5, it will be 0.57 sigma y. Compare this with what we got for Tresca. From Tresca criteria gave tau y to be sigma y by 2. Okay. Thus, even though we agree on the uniaxial yield stress, we will not agree on the pure shear yield stress. Okay. Now, let us do the reverse, just like what we did for Tresca criteria. Let us assume that we find kappa from the shear stress. Okay. Let us assume we found kappa from the shear stress. So, kappa square tau y pure shear square must be equal to kappa square. In other words, kappa should be tau y pure shear. Okay. Now, I want to predict what is it for uniaxial test. Okay. For uniaxial test, I found k to d to be sigma 1 uniaxial whole square by 3. For uniaxial test, I found k to d to be uniaxial square stress divided by 3. Okay. So, basically now I will have, now what I am doing is I am using shear pure shear stress state to find kappa and use it to predict the uniaxial yield stress. Okay. So, k to d for uniaxial yield stress is sigma uniaxial whole square by 3 from what we computed above. This should be lesser than or equal to kappa square, which is sigma pure shear y the whole square. Okay. So, this implies uniaxial yield stress should be equal to square root of 3 times tau y pure shear. Okay. Contrast this with Tresca criteria. In Tresca criteria you got it as 2 times, this is nothing but 1.73 times tau PSY. Okay. In Tresca criteria you got it as sigma y uniaxial to be 2 times tau y pure shear. Okay. So, basically there is a difference between vonMises and Tresca. It might agree at some points, but there will be deviation at some other points. Okay. Next, let us understand what happens, what are the other interpretations of vonMises criteria. Okay. We saw that k to d was given by 1 by 6 sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 1 whole square. In lecture 9 we saw that this is nothing but 2 by 3 times octahedral shear stress squared. Okay. Octahedral shear stress is the shear stress that occurs in the octahedral plane, that is a plane that makes equal angles with the principal axis, okay, principal directions. Okay. So, we saw all those things in lecture 9. Okay. So, now, so I can interpret the vonMises criteria as the octahedral shear stress being limited to a particular value of kappa square, okay, kappa tilde square. This kappa and the previous kappa are different because I have factor 2 by 3 coming in there for the octahedral shear stress. Okay. So, I can view it as some octahedral shear stress being limited to a particular value. This defines the plane in which the body will fail. The body when it obeys vonMises criteria will fail in a plane which makes equal angle with the principal directions, whereas in Tresca criteria it will fail in a plane where the maximum shear stress occurs. Okay. So, there is a difference. So, the plane of failure in vonMises and plane of failure in Tresca would be different. Okay. So, if I interpret it like this, the failure plane is the octahedral plane, octahedral plane, where octahedral plane is the plane that makes equal angle with the principal directions. Okay. Now, let us see what the octahedral plane is for uniaxial state of stress. Okay. For uniaxial state of stress, I know the prescribed coordinate system is the principal direction also, because state of stress is sigma 0 0 0 0 0 0 0 0. I know that my prescribed x, y, z axis to represent the problem is the principal axis. Okay. Now, a plane which makes an equal angle with all this would be this plane which makes an angle cos inverse of 1 by root 3 with these axes. It is this plane about which the failure would occur, okay, wherein all these angles are cos inverse 1 by root 3. Okay. So, there will be 8 such planes, one on this direction, one in that direction, and you can imagine that there are 8 planes, hence it is called as an octahedral plane. So, any one of those 8 planes, it might slip or slide in those planes. Okay. Okay. Now, so we saw for Tresca criteria this failure plane was 45 degrees to the x axis, right. If I am applying, if my body was like this, if my rod was like this, and if I applied a uniaxial stress sigma here. Then the failure plane now would be this octahedral plane, which makes equal angle with all the x, y and z axis, whereas the Tresca criteria it will be a plane which made 45 degrees with respect to the x axis. Okay. So, that is the difference between the failure planes of octahedral and Tresca criteria. Okay. Now, there is one more interpretation of this octahedral shear stresses, okay, that is vonMises criteria can be interpreted as the limiting value of the distortional stored energy. Okay. Now, let us define another quantity called distortional stored energy. Okay. That is, this is the energy caused by the deuteric stress. So, this energy we will denote it by use of D. I will define the complementary strain energy, complementary distortion stored energy to be more specific. Okay. So, this will be nothing but 1 plus nu by E into trace sigma D whole square. Okay. Now, you know that K to D is nothing but 1 half of sigma D the whole square. So, this is nothing but 2 times 1 plus nu by E K to D, since K to D is 1 half trace of sigma D square, trace of sigma D squared. Okay. So, you find that the distortion complementary distortional stored energy is proportional to K to D. Okay. So, complementary distortional energy is proportional to K to D, and hence vonMises criteria can be interpreted as a criteria which says that when the complementary distortional stored energy reaches a particular value, the material fails. Okay. Why do you want to interpret it as complementary distortional stored energy? The reason is, you know that to form new surfaces when a crack or when a sliding occurs, you need energy to form a new surface. So, that energy only when it is available a new surface or a crack would form. Okay. So, which means the energy strain energy is the one which should govern when the crack forms. Okay. So, in that perspective vonMises criteria is also interpreted as criteria wherein the complementary distortion strain energy reaches a particular value, the failure begins to occur. Okay. So, you can say that when UD star is less than or equal to some kappa hat squared, the failure occurs. Okay. So, one criteria you have 3 different explanations for the same criteria. One, it is just comes from the invariant theory of these stresses. Second, it is interpreted as the octahedral shear stress not exceeding a particular value. Third, the same criteria is interpreted as the distortional stored energy not exceeding a particular value. Okay. So, these are 3 different interpretations of the same vonMises criteria. Okay. Next, let us go ahead and construct the failure surface for vonMises criteria. Next, what we are going to do is construct failure surface for vonMises criteria. Okay. Now, as before, I am going to look at a plane state of stress, plane stress state, which we saw can be represented in terms of sigma 1 0 0 0 sigma 2 0 0 0 0. Okay. And hence I am going to retain the first usage of the vonMises criteria, that is K to D must be less than or equal to kappa square, which will imply that sigma 1 minus sigma 2 whole square plus sigma 1 square plus sigma 2 square by 6 must be less than or equal to kappa square, which we will write it as sigma y whole square by 3. In other words, I have 2 sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2 must be lesser than or equal to 2 times sigma y square. Okay. So, this in other words boils down to sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 must be less than or equal to sigma y the whole square. Okay. Now, what does this equation represent? This equation represents that of an ellipse inclined about an axis, okay, not about sigma 1 sigma 2 axis, but inclined to sigma 1 sigma 2 axis. Let us see how to construct that ellipse. Let us say this is sigma 2 axis, this is sigma 1 axis. I know that when sigma 2 is 0, sigma 1 would be sigma y, and when sigma 1 is 0, sigma 2 would be sigma y. The uniaxial state of stress points, I know this point and I know this point, this should be sigma y and this should be sigma y. And when sigma 1 equal to sigma 2, if sigma 1 is equal to sigma 2, I know that the above equation reduces to sigma 1 equal to sigma 2 equal to sigma y for the maximum stress states. Okay. Sigma 1 equal to sigma 2, this sigma 2 square and sigma 1 sigma 2 gets cancelled, sigma 1 has to be equal to sigma y. Okay. So, I have sigma y point which I have to pass through. Okay. These are the 3 points I know of which are on the ellipse. Okay. Similarly, I have 3 points in compression. Tension or compression does not make a difference, just like in Tresca criteria, and hence what happens is in compression also I have minus sigma y and sigma 1 equal to sigma 2 equal to minus sigma will give me it is minus sigma y again, minus sigma y comma minus sigma y. These are the 6 points by which the curve has to pass through. Okay. Next, let us consider a case wherein sigma 1 is equal to minus sigma 2, okay, equal to tau, then I will get it as 3 tau square must be less than or equal to sigma y whole square, or tau must be equal to 0.57 times sigma y, that is 1 by root 3 times sigma y. Okay. So, I can sigma 1 equal to minus sigma 2 equal to tau is a 45 degree line, this is a 45 degree line here, and I know the point on this line, and I know the point on this line. Okay. So, now the ellipse has to pass through all these points. Okay. So, this is the yield surface, this is the yield surface for vonMises criteria. It is in the form of an ellipse with sigma 1 equal to sigma 2 and sigma 1 minus sigma 2 45 degree rotated ellipse. Okay. So, let us see how it is 45 degree rotated ellipse. Let us do sigma 1, let us rotate let us say x star is x plus y by root 2 and y star is x minus y by root 2, then x star squared by a square plus y star squared by b squared would be x square plus y square plus 2 xy by 2 a square plus x square plus y square minus 2 xy by 2 b square equal to 1. Okay. So, now you adding this, you get x square by 2 a square, so 1 by 2 b square plus y square into by 2 1 by a square plus 1 by b square minus 1 by b square minus 1 by a square xy equal to 1. Okay. Now, comparing the coefficients of sigma 1 square, sigma 2 square and sigma 1 and sigma 2, we want 1 by 2 1 by a square plus 1 by b square to be 1 by sigma y the whole square, and we want 1 by b square minus 1 by a square to be 1 by sigma y square. Okay. So, we got these two equations by comparing the coefficients of x square y square x y with sigma 1 square, sigma 2 square and sigma 1 sigma 2. Okay. Now, let us add these two equations. 2 by beta square should be equal to 2 by 3 by sigma y the whole square, right. Okay. So, that will imply b is should be 2 by 3 sigma y the whole square. Okay. Now, substituting this, b square is 2 by 3 sigma y whole square. Now, substituting this in here, you will get it as 3 by 2 sigma y whole square minus 1 by a square equal to 1 by sigma y square. In other words, 1 by a square is 1 by 2 sigma y whole square, or this implies a square is 2 sigma y square. Okay. 2 by 3 sigma y whole square and a square is that. So, substituting that back in our equation, you get x square by sigma y squared plus y square by sigma y squared minus x y is equal to 1, or in terms of x star y star squared, it will be x star by 2 sigma y whole squared plus y star by 3 by 2 y star by sigma y the whole squared must be equal to 1. Okay. So, that gives us the equation of this ellipse. Okay.